Well, we now discuss the sort of debris of the solar system in the form of asteroids. In another video, we'll talk about comets. This one, asteroids and meteorites. And we're, again, way below planet-sized or moon-sized object. Well, sort of below moon-sized objects, but the asteroids are an interesting group of objects and can give us clues about the history of the early solar system. We have an asteroid belt that's in between the orbit of Mars and Jupiter. As these objects were first seen in the early 1800s by telescopes, they appeared as just points of light that were moving through the constellations. So the astronomers knew that they were orbiting the sun, but there was no disk. But because they're orbiting the sun, at first they got to be called minor planets. They were not reflecting as much light as the other planets, like Uranus or Neptune or Saturn. So they're minor planets, and now we don't use that term too much. We'd call them the asteroids. We have a belt here, and there could be 1 million of these asteroids in the orbit between Mars and Jupiter. I believe the orbits of about 300,000 are known as to what path the asteroid takes. So we have this main collection in the asteroid belt between Mars and Jupiter. There are also a group of asteroids ahead of Jupiter by 60 degrees and behind Jupiter by 60 degrees. These turn out to be stable orbit positions with Jupiter's gravity and the Sun's gravity creating a situation where pieces of rock, the asteroids, can kind of gather and be a stable situation. So those are our main group, and the main group is the asteroid belt in between the orbits of Mars and Jupiter. So the asteroids orbit in the same direction that the planets orbit the sun. They are very near the ecliptic, although they're not totally in the ecliptic, not in the plane of the planets. And there are some families of asteroids that have orbits that are inclined to the ecliptic. And it's thought that those are results of collisions and the fragments then continuing on in that kind of position of a certain inclination to the orbits. We also have asteroids that come near the Earth. You can see some dots in here, and those, of course, are interesting, as we'd like to have some early warning if there's some significant size piece of rock that's going to come close to the Earth. Again, when an impact occurs, the crater is about 10 times the size of the rock that made the crater. So if there's an asteroid that's 1 kilometer in size, it could make a crater 10 kilometers across. That's about 6 miles. That's fairly significant if that would include a city. So the near-Earth asteroids are kept track of, and there's about 5,000 that have their perihelion inside the Earth's orbit, their closest approach to the Sun inside the Earth's orbit. So there's a lot of dots on this. What would happen if all the material would be gathered into a lump, would it be a planet if all this material could be gathered? And the answer is no. The estimate is it would be smaller than our moon if all these bits of rock and ice would form together. And it's quite possible that there could have been a small object here gathered together, that the gravity of Jupiter is influential in this region and keeps things it's kind of stirred up and in motion into moving into different orbits, and somewhat prevents the collection of the asteroids into a single object. Some photographs of comparing the moon with Pluto. Pluto's smaller than our moon. Ceres, the largest of the asteroids and really a minor planet, smaller than Pluto. Vesta, an asteroid, and there's kind of a little trend here as well. In the asteroid belt, the asteroids that are on the inside, closer to Mars, tend to be more rocky, and the asteroids that are in the outer belt tend to be more icy. It's sort of a transition region between the terrestrial planets and the Jovian planets. as we move outward there. So there's a little survey. Of course, spacecraft have flown through the asteroid belt. The two Pioneer, the two Voyager, the Cassini, the Galileo spacecraft to Jupiter, the Juno spacecraft en route to Jupiter now, the New Horizon going to Pluto. So spacecraft can fly through the asteroid belt, and there's no pilot on them like Star Wars to zoom around, zip around, and avoid the asteroids. There's just a lot of empty space in space, and there's enough space between the asteroids. There's no problem of hitting one. So the science fiction movies make it a little more dangerous than what it actually is. Some of the asteroids have moons, and of course when a moon is present, then the mass of the asteroid can be calculated by a study of the orbit size and the time for an orbit. But 33 miles long for this particular asteroid. It's not typical for the smaller asteroids. These are not spherical shaped. They don't have enough gravity to form a spherical object. But there are asteroids that are spherical, that are larger. Another example here, you can see lots of impacts that have happened, and just a little preview. What do you think might happen when an impact occurs and rock is blasted out of this crater region? Well, that rock usually doesn't come back to the asteroid. The asteroid's gravity is very small, so this rock flies off and we can have a meteorite land on the Earth. So recently there was the Dawn mission to the asteroids. It launched in 2007. It did not use rocket fuel. Instead, it used more of an electrical engine that used electrical repulsion to push particles out the rocket nozzle. It's low force, but it's cheap, and it's an efficient way to navigate in the outer solar system if you're not in a terrible hurry. So arrived at this asteroid Vesta in 2011 and orbited for about a year, taking photographs, making measurements of the minerals and other measurements of the characteristics of the asteroid. And it's en route now to the dwarf planet Ceres, again in the asteroid belt. The artist drawing conception here showing this ion engine, solar panels to capture electricity and help in the operation of this ion engine. So there's a little description here of the ion engine is kind of a proving ground itself on this mission, and that the ion engine would work and could be restarted, turned off and started on again. So studying the geology and composition of the asteroids and giving us some clues on when they formed and how they formed. This asteroid's material, as I say, is probably a remnant of the early solar system that didn't form into an object. Some of them are large enough that they did melt and have differentiation and iron in cores and more rocky crust, but I want to study these early objects. So Ceres, you can see it's big enough that gravity has made it into a sphere. The left image there, and Vesta, also nearly a sphere. Not quite as big, but the Hubble telescope can image these objects. It does turn out that Vesta has minerals on its surface that indicate lava, a basalt type material. And Ceres is more icy, a mixture of rock and ice. Again, as we move towards the outer part of the asteroid belt, more rocks and ices. The inner part of the belt, more these rocky type asteroids. And a little description here of asteroid. And asteroid, it's a point-like in a telescope, point-like light viewed there, not a disk. And we're located in between Mars and Jupiter for the main asteroid belt. There is a little blurring that's going on between asteroids and comets, and that these objects in the asteroid belt, some of them have significant amounts of ice in them, and we usually associate that with comets. So again, inner belt, we would have more of the rocky material, and then the icy objects in the outer belt. these objects big enough to be round, some would call them protoplanets, in that they were starting to become a planet, but their gathering of material got interrupted. Notice there's some gaps in the asteroid belt called Kirkwood gaps, and the idea here is that Jupiter is on the outside here. So what will happen if we have a rock in this gap and it orbits, let's say, 3 times while Jupiter orbits 1 time? Well, every third time around, Jupiter is going to be close here and give a little pull, give some energy to this piece of rock. That's going to disturb its orbit so that it won't stay in the orbit in this gap. So Jupiter creates these gaps in the asteroid belt with resonances. When the asteroid orbits 2 times or 3 times and Jupiter orbits once, we get that repeated pull, that resonance, repeated pull, and it moves the rock out of that orbit, and we get gaps in the asteroid belt, very similar to the gaps in the rings of Saturn. So I've already gone through that. We'll go on to our next slide here. So Ceres, Pallas, Vesta, big enough to be round, and the smaller asteroids just have an irregular shape. They've accumulated some material, but their gravity is not big enough to form into spheres. So, a little tour of Vesta. Again, as I say, in the early 1800s, these asteroids started to be discovered. And again, some mythology going in here with the names. So 265 kilometers for the radius here. And if you want to convert that to miles, multiply by 0.6, and it's somewhere in the ballpark of 160 perhaps miles. I don't have a calculator, so you should go ahead and do that. But third largest asteroid and second most massive. It's made of dense material, rocky material instead of the icy. It is differentiated. It has a metal type core and lava on the surface. And we believe it was formed early in the solar system. Ceres, discovered in 1801, it's the largest and most reflective of, I don't know if it's the very most reflective, but it's very reflective, has more of the icy surface, so it's brighter. And its radius here larger, 950 kilometers, so talking upwards of 600 miles across for that object. And can't see surface features right now, but certainly the Dawn spacecraft, when it orbits Ceres, will give us some better views of the surface. Will there be craters, or is the surface so icy and soft that craters can't form a definite impact? And as far as we know, no meteorites. A meteorite found on the Earth, you can study its surface properties and how it reflects light, and then compare that to light reflected from the asteroids still in orbit between Mars and Jupiter, and determine what type of asteroid the rock came from. So no pieces of ice survive passage through our atmosphere and land on the ground to be picked up. That's from a thunderstorm, hail. Again, Ceres and Vesta. And now Vesta from the Dawn spacecraft, orbiting for about a year, as I say, and there's some interesting features around the midpoint here of the asteroid and other craters, but some nice streaks going all the way around the asteroid. And just another side here, some more craters being visible. A little bit of a fresher crater here with its rays still being in evidence. Another view, and then the mapping of hydrogen on Vesta, would indicate that there's probably water ice underneath these regions where the concentration of hydrogen is stronger. So again, there's a blurring of the definitions and composition between asteroids and comets, that there's now more ice is being found on the asteroids than what was thought to exist in the past. They're not just pure rocks. Another asteroid here, Itokawa, and you can see the shadow of the spacecraft that took this image. That's kind of interesting. It's, there's not a alien-built spaceport on the surface of this asteroid. That's the shadow of the spacecraft from the Japanese space agency. Is actually the Japanese Aerospace Agency is the operator of that spacecraft. And then talking about near-Earth asteroids and the discoveries of even the little ones, as we increase in time here, our telescopes are getting better at searching out the debris of the solar system that crosses the Earth's orbit. As we look at larger of these near-Earth asteroids, kilometer size and larger, you can see that the number of discoveries is decreasing. That gives us some confidence that we're getting a more complete catalog of these very dangerous pieces of rock that would make a big impact on the Earth. So it's not down to zero yet. There's still more to be discovered, more work to do, but we are discovering quite a few of the near-Earth asteroids. Now, meteors. As we have the little bit of sand or small piece of rock come into our atmosphere, about 50 miles or a little higher, there's enough air that the friction here, there's a warming that goes on, and it's the gas in our atmosphere that's being warmed and energized. The light you're seeing here comes from atoms in our atmosphere, molecules in our atmosphere. The light does not come from the hot piece of sand that's moving through the atmosphere. It doesn't have enough surface area to generate a lot of light, but it's energizing a lot of molecules along its path, and we get this meteor in the atmosphere. Before the little bit of material comes into our atmosphere, in space it's called a meteoroid. And on the ground, if it survives, if it doesn't melt away as it goes through the atmosphere, then it's a meteorite. So a meteor, the glowing gas, the light that we see in the sky. Meteoroid while it's in space, and meteorite while it's on the Earth. So those are our terms here. Meteoroid, meteor as it goes through the atmosphere. If it survives and lands on the ground, meteorite. Then there are times when there are extra meteors seen in the sky, meteor showers. When the Earth goes through a pack of debris that's orbiting the sun, as the Earth goes through that debris field, then there will be a meteor shower where there's an extra abundance of grains of sand and small pieces of rock entering our atmosphere. It'll look as though the meteors are coming from one point on the sky. That's called the radiant. And if you live in a place where it snows, then if you would drive at night with your headlights on, you would see snowflakes kind of do this same thing. It appears that the snowflakes come from a certain point out ahead of you. They're not actually generated in our atmosphere, or the snow is not generated right in front of the car, but it's kind of a perspective thing as you're going into the stream of meteors. We do live on a moving Earth, and the Earth is carrying us through the pack of debris that's orbiting the sun. So we get this effect, and it's repeated. Each year we get the Perseid meteor shower, where the radiant's in the constellation of Perseus. We get the Orioid meteor shower, where the constellation of Orion is the radiant. We get the Leonids, where the constellation of Leo is where the radiant is located. So we have this material coming into us, and I don't know if it's not a significant amount of material in terms of how much mass it adds to the Earth, or it's not causing the Earth to increase in size. It's apparent in the sky. We get a bright light, but it's not adding a lot of mass to the Earth. As far as the meteors that are found, and let's go on to that, the meteorites, you can see evidence of melting as it's gone through our atmosphere and pits that are around here. And most of the meteorites that are discovered on Earth are iron, but that's not the most abundant type of asteroid where these meteorites come from, get chipped off by collisions. The more abundant type are the mixture of silicate materials and carbon, kind of rocks and carbon, is the most common material. in the asteroid belt. Then there's another group of asteroids that are more stony without the carbon, the silicate. And then more rare are these iron type, iron and nickel asteroids, or yeah, iron nickel asteroids in the asteroid belt. And they're only easy to find on the Earth because they look much different than an Earth rock. The silicate meteorites, or the silicate and carbon, the carbonaceous meteorites, they kind of blend in with rocks on the Earth. So where might you go if you wanted to find rocks that blend in, meteorites that blend in with rocks on the Earth? Where would you go such that there aren't any rocks? Well, you might go to a desert where it's all sand, or you might go to the Antarctic and look around on the ice. And that is a good search field for meteorites, for the stony type meteorites. And I ought to let you know too that there's historical references to meteorites. And if you go to the New Testament in Acts 19:35, I'll read that. The city clerk quieted the crowd and said, "Fellow Ephesians, doesn't all the world know that the city of Ephesus is the guardian of the temple of the great Artemis and of her image which fell from heaven?" So these people had picked up a meteorite and turned it into an idol. So don't do that, but you can pick up meteorites and make a profit. Just for some of the websites and eBay that I looked at, it's about $500 a pound when you find a meteorite and it's documented, and take photographs of it before you pick it up, and pick it up with gloves, put it in a plastic bag, and then perhaps you can get $500 a pound. So a little bit further here, as meteorites are sliced open, there's a nice crystal structure that indicates for slow cooling took place. So this meteorite came from a larger object, 100 kilometers in diameter or so, where the cooling was not real rapid, but a little bit slower than crystals can grow. But a nice pattern for that. Another couple examples of meteorites, so you'd have some trouble distinguishing this from ordinary Earth rock. And it takes a little practice. I've never really gone out meteorite hunting, but you might want to just keep your eyes open, and if you do find one, that would be great, and get it sort of verified by an expert. I'm not an expert, but you can look for that. I would ask you, where do you think the iron nickel meteorites would come from? Well, we have collisions of the asteroids in the asteroid belt. So presumably there was a collision with a larger body, the body that became differentiated, where the iron and nickel sunk to a more collecting point, so you get more of a pure material rather than just a few grains of iron mixed in with a lot of rock. So an evidence of a differentiated body in the asteroid belt that had collisions. And as meteors come through the atmosphere, if there are enough cameras tracking the meteor, astronomers can trace back the orbit of the material and determine where it came from. And again, that has been done, and verifies that many of the meteors have their origin in the asteroid belt. So with that, I'm going to let you just keep reading on your own and write down some questions. Oh, maybe one other thing. When would you go looking for meteors? When would be a good time? It turns out after midnight. So after midnight, you're on the side of the Earth that's going forward in its orbit before sunrise. And in that situation, the Earth catches up with slow meteoroids, and fast meteoroids as well, more likely to enter the atmosphere. Before midnight, only the fast meteoroids are going to enter the Earth's atmosphere. The Earth is moving away from the slower ones, so we don't get quite as many coming into the atmosphere. In addition, when we're moving towards the meteoroids, instead of them having to catch up with us, if we're moving toward them after midnight, before sunrise, then the collision type speed is greater. And with greater speed, there's more energy to energize more molecules in our atmosphere, so you get a bigger streak of light and more readily seen by the observer. So if you're going to look for meteors, try to stay up late, after midnight, and do your viewing. Okay, time for me to sign off. Let you write down some of your own questions.